All right, I want to give you guys a little show and tell on a force table. And a force table is a lab. If we did this lab, it would be, you guys would walk away from this lab going, man, I totally get vectors. I understand what vectors are. So I've made a little drawing here, and this is kind of a vector diagram. I've got one vector pointing up in the y direction, and I've got another vector pointing off in the x direction, and then I've got a resultant vector. Now you would recognize this like in math classes. This is just a graph, Mr. A, and what you've done is you've plotted this. Now I bet that if I asked most of you guys what would be the length of this line, if the angle between the resultant vector and the x-axis, say, was 45 degrees, if this was 45 degrees, and this was splitting the difference, I bet most of you could look at this graph and, like on your SAT, say, oh, well, the length of that line would be the length of this squared plus the length of that squared, take the square root, right? So this is your C is equal to a squared, the square root of a squared plus b squared. So you guys know that Pythagorean theorem thing, like inside and out, right? So this is just the resultant vector of these two forces, right? So what I want to show you now, I'm going to take this off. I'm going to show you. Let's just pretend now. This is a force going in the y direction. This is a force going in the x direction. The resultant force is that force that's coming off in this one. So like if this is wind blowing you this way and wind blowing you that way, the result is that you're going to be going this way. Now, in order to counteract that force, all I have to do is hang the right amount of weight over in this direction. And these tables are set up with angles, and it's got this little ring. So if it's touching your ring, the forces aren't balanced. If the forces are balanced, then the ring will be perfectly centered. So what I've got hanging off of each edge, on this string is a 50-gram weight here, and I've got a 50-gram weight here. And the force that's being pulled on this string is the mass times the acceleration of gravity. So over here I've got a 50-gram mass times the acceleration of gravity, right? So what do I need to counteract that? And you can simply use vector addition in order to calculate how much force or how much mass you're going to have to put on this end in order to balance it out. Obviously, the 50-gram mass isn't enough. You've got 50 here, 50 here. You're going to need what? What is it? 1.4 times, no, 1 point, is the square root of 1 point, whatever that Pythagorean, you're going to need more weight over here. So if you do the math, and I'll take a still picture up and put it on the video, but if you do the math, it calculates out to be like 71 grams. So here's 50 grams, here is 10 grams, wasn't enough. Here's 10 more grams, wasn't enough. Oh, it came off at 70 grams. In order to make this perfectly centered, I've got to add like one more. So my experimental error, I've got 71, calculated it. Oh, 71. No, this is actually, let me see here. That was 70, this is a 2-weight gram. So I'm like 1 gram off. So my experimental error is like 1%. And you could say, well, Mr. A, there's some mass associated with the string, so you got to add that too. So I could have you guys do a lab like this, but I just probably not going to have time for that. But I just wanted you to see the force table and see how it relates to vectors. Right? Got it? Thank you for watching. Buy my mixtape. Right? All right.